Thanks for joining my talk today. My name's Edwin Locke, and I'm going to talk about how to learn strong substitutes demand correspondences when given access to a demand or valuation oracle. This is joint work with Paul Goldberg and Francisco Marmolejo. Suppose we want to run an auction with n distinct goods. Our goods are indivisible and we allow multiple units of each good. Every bidder who participates in the auction has certain demand preferences, which means that at any given prices for goods, they want some bundle of goods. If prices are too high, this might be the empty bundle. A bidder could also be indifferent between different bundles at some prices. The demand correspondence maps each price vector to the set of bundles that the bidder demands at these prices. In this talk, I present a systematic procedure for bidders to represent their demand in a compact way. This allows bidders to participate in sealed bid auctions such as the product mix auction introduced by Paul Klemperer. Typically, the demand correspondence is defined by means of the valuation function, which maps every possible bundle of goods to the value that bidders have for it. Although I've written out the classic definition of demand for completeness, we're going to use a novel geometric characterization of demand introduced by Baldwin and Klemperer instead. This characterization tells us that any quasi-linear demand correspondence partitions price space into a weighted integral polyhedral complex. On the right-hand side, we see an example of a simple demand correspondence on two goods, which we'll call 1 and 2. Price space is clearly partitioned into polytopes, and each of these polytopes corresponds to a region in which some bundle is demanded. The bundles demanded by each polytope are represented by a pair of numbers that indicate the number of units of each good. For example, the bundle in the bottom left-hand corner contains 1 unit of each good. Throughout this talk, we assume that bidders have strong substitutes demand preferences. Strong substitutes preferences can be defined in many ways, but Baldwin and Klemperer give a particularly elegant geometric characterization. A demand correspondence is strong substitutes if and only if the facets of the polyhedral complex are normal to a unit vector, or the difference between two unit vectors. When we have only two goods, this means that facets can only be horizontal, vertical, or they can have a slope of 1. Using this geometric characterization, we can immediately see that the example demand shown here is strong substitutes. If we consider strong substitute demand preferences from this geometric point of view, a natural question is to ask how we can represent this weighted polyhedral complex in a compact way. The bidding language originally introduced by Klemperer in 2008 as part of the product mix auction provides a parsimonious way to define demand using a list of weighted vectors in price space. The product mix auction was designed for the Bank of England during the financial crisis of 2007 and 8. It's still used regularly by the bank to provide liquidity to financial institutions. How does this bidding language work? Every bidder submits a list of bid vectors, together with a positive or negative weight for each vector. In this talk, I'm going to restrict myself to demand correspondences with two goods, as things get rapidly less intuitive in higher dimensions. But the same principles generalize to any number of goods. Okay, so let's consider the case where a bidder submits a single bid vector at 6,6 that has a positive weight. Then the good that this bid demands depends on the region in which the prices lie. At prices that lie in the bottom right-hand region labeled 0, 1, the bid demands 0 copies of good 1 and 1 copy of good 2. Similarly, if prices lie in the top left-hand region, the bid demands a copy of good 1 and 0 copies of good 2. And finally, if the prices lie in the top right-hand region, the bid demands nothing. However, if a price vector lies on a facet that divides 2 or more regions, the bidder is indifferent between the bundles in the local neighborhood of these prices. Now, suppose a bidder submits 2 positive bids. In this figure, our 2 bids are at 6,6 and 4,2. In order to determine the bidder's overall demand, we consider each bid separately, and then add up their individual demands. At prices P, for instance, both bids demand a copy of good 1, so total demand is 2 copies of good 1. At prices P dash, on the other hand, the first bid B demands a copy of good 2, and the second bid B dash demands nothing, so overall demand is 1 copy of good 2. In this figure, every convex polytope is labeled with a bundle that it uniquely demands. In general, if a bidder submits many bids, the total demand is obtained by summing up the demand from each individual bid. In this way, we can construct polyhedral complexes with arbitrarily many polytopes. So far, we've only seen positive bids, but some demand correspondences require bids with positive and negative weight. Our original example on the left, for instance, requires 3 positive bids and 1 negative bid. These bids are shown on the right-hand side. The positive bids are solid and the negative bid is hollow. Negative bids work in the same way as positive bids, except for the fact that they remove rather than add a copy of the good they demand from the overall demand. Baldwin and Klemperer have established that any strong substitute's demand can be expressed as a list of positive and negative bids. This makes the product mix bidding language appealing for sealed bid auctions, where all bidders submit their entire preferences before the auction is run. However, it's worth noting that the converse of this theorem does not hold. Not every list of positive and negative bids induces a valid demand correspondence. Suppose we want to run an auction using the bidding language that we've just defined. Any bidder who wishes to participate will need to submit the bid list that corresponds to their demand. But if the number of goods is large, or their demand is complex, it's not immediately clear how a bidder might construct this list in the first place. It's even possible that a bidder does not have a comprehensive geometric understanding of their demand in the first place. However, we do assume that a bidder can tell us, for any fixed prices, some bundle that they demand at these prices. Formally, we say that the bidder can answer a demand oracle. In order to help the bidder, we want to solve the following question. Given a demand oracle, can we find an algorithm that outputs the bid list corresponding to a bidder's demand? At this point, it's worth noting that we can simulate a query to a demand oracle using a polynomial number of queries to a valuation oracle. This uses standard results from discrete convex optimization. In other words, if we give an oracle access to the demand on the left-hand side, we want to design an algorithm that returns the 4 bids shown on the right-hand side. We evaluate any such algorithm in terms of its query complexity, which we measure in terms of 3 parameters: the number of goods n, the number of bids b, and the number of bits required to store each entry in the bid vector. We have 3 main results that shine light on the computational complexity of this problem. Firstly, in the case where all bids are positive, we have a linear time algorithm for learning the bid list. This algorithm is relevant because the Bank of England currently only allows bidders to submit positive bids. We're not going to look at this algorithm today. In practice, we see that many realistic demand correspondences require positive and negative bids. In this case, we show a superpolynomial lower bound on the query complexity. Intuitively, this follows from the fact that negative bids can cancel out facets with their negative demand, which means that we may have to query in the vicinity of this negative bid to detect its presence. If we quickly go back a couple of slides to our example, we can see, for instance, that the horizontal facet of the leftmost positive bid is being cancelled out by the negative bid from 4,4 onwards to the right. Accompanying this result, we also present a superpolynomial lower bound on the query complexity in this case. When the number of goods is fixed, we see that the upper and lower bound that we achieve almost match. Let's first take a look at the algorithm for learning positive and negative bids. Suppose we want to learn the demand shown on the left-hand side. Our algorithm conceptually proceeds in 2 stages, which are illustrated from left to right. In the first stage, it learns all the hyperplanes that contain a facet of the polyhedral complex. In the second stage, it then considers all the vertices that arise from intersections of hyperplanes and checks whether there is a bid at these locations. Let's take a closer look at the first stage. First, we place 4 boundary hyperplanes to form a bounding box that contains all bids. This is shown on the right-hand side. At this point, we haven't learned any hyperplanes yet. We first query demand in every corner of the bounding box. If there are any hyperplanes to be learned, demand will differ for at least 2 of these query points. This means that these query points are separated by some hyperplane, and we can use binary search between these 2 points in order to find it. In our example, for instance, we see that the top 2 query points have different demand. If we binary search between them, we will find one of the 2 vertical hyperplanes running through prices 0, 2 and 0, 4. Now suppose we found the hyperplane through 0, 2. This hyperplane divides price space on the right-hand side into 2 polytopes. We now perform demand queries in the corners of each polytope. Note that we only need to perform queries in the new corners as we can remember the old query results. As before, we note that there are new hyperplanes to be learned if and only if demand differs at 2 query points that lie in the same polytope. This procedure is repeated until all query points that lie in the same polytopes demand the same good. At this point, we've found all hyperplanes. The second stage of the algorithm considers all vertices that can be obtained by intersecting these hyperplanes. At each vertex, we can check whether there is a bid at this point. We do this by performing a so-called superquery around the vertex, which gives us full information about the local demand around this point. But if we look closely, we notice that we already queried in every corner of the polytopes touching the vertex in stage 1. This means that if we've stored the results of the queries we made in stage 1, we don't need to make any new queries whatsoever in stage 2. This allows us to establish the query complexity of our algorithm. We only need to count the number of queries that are made in stage 1. So first of all, let's see how many hyperplanes we might have to learn. There are B bids, and each bid owns at most n choose 2 facets. As every hyperplane contains at least 1 facet, we know that there are at most B times n choose 2 hyperplanes. There are only 2 reasons that our algorithm makes demand queries. Firstly, it queries in the corners of all the polytopes that arise from the hyperplanes that we've learned. We can upper bound the total number of corners by the term on the left-hand side. The second reason why our algorithm makes demand queries is when it performs binary search between 2 query points to find a new hyperplane. As each binary search costs log m queries, and we learn at most b times n choose 2 hyperplanes overall, the right-hand side bounds the number of queries that binary searching incurs. We see that if the number of goods is constant, we get a polynomial algorithm. I mentioned earlier that we have a superpolynomial lower bound for learning bid lists containing positive and negative bids. Let's take a look at how this superpolynomial lower bound is achieved. First of all, we introduce a gadget consisting of 2 to the n plus 1 positive and negative bids. This gadget only changes demand locally. To illustrate how the gadget works, consider the demand correspondences on the left and the right. In 2 dimensions, the gadget consists of the 8 bids contained in the red perimeter on the right. We see that demand outside this perimeter is identical to the left and the right, which means that the gadget bids are undetectable if we only query outside the convex hull. This gadget allows us to design an adversarial game where the adversary places the gadget at exactly 1 out of many locations. In order to learn where the gadget is, the player either needs to query inside the gadget or make queries inside all other potential gadget locations. This leads naturally to the lower bound shown on this slide. If the number of goods is held constant, this almost matches the bound achieved by our bid learning algorithm, which was O of b to the n plus log m. To conclude, our algorithm constitutes the first systematic way for bidders to participate in product mix auctions. But our results may also be interesting beyond the confines of auctions. Firstly, the strong substitutes bidding language is really a demand language and can be applied to exchange economies more generally. Our lower bound also gives us new insights into the computational complexity of eliciting demand. Moreover, another interesting topic beyond the scope of this talk is that bids in this language can be generalized to express any gross substitutes preferences, and our algorithms can be modified to learn these generalized bids. This allows bidders to express richer preferences. Thanks for attending my talk. If you have any questions or comments, please do get in touch.